Okay. So my name is Dan, and in the next 10 minutes, I'm going to talk about hydrodynamic stability of cold streams in hot halos. This work is done in collaboration with Nirman Delker from Hebrew U and with others. So since I only have 10 minutes, I'll be very quick about compressible Kelvin-Helmholtz instability. The main things you need to know about tackling it using analysis and numeric simulations. We used Ramsey's for this work. I'm going to compare the analysis with the simulations and then talk about some astrophysical implications. So very briefly, the background for this, the motivation for this is our knowledge today tells us that for high redshift massive galaxies, incoming cold streams contribute a large part of the gas accretion rate. So in a typical high redshift massive galaxy, we will have a virial shock shown here as the more or less white circle. That's more or less the virial radius. But penetrating into that virial shock, we have cold flows. These three streams here, the color map is gas density. And so these streams penetrate well into the virial radius and contribute a large part of the gas accretion rate. And what you see in the next picture is, well, in the central region, we have the quote-unquote messy region where the streams do all sorts of interesting things. They interact, they maybe form clumps, but at larger radii, they really don't do anything interesting. They just flow more or less radially. And this, one could argue, is at least in part due to the low resolution in this picture. So in a typical cosmological simulation, you would have the width of the stream resolved to within, say, 10, give or take, simulation cells. And you really can't expect to see any interesting hydrodynamic instability with that kind of resolution. So what we propose instead is to study this problem of interaction of the stream with the surrounding halo material using simple toy models in order of increasing complexity until we build our understanding of the whole problem from the bottom up. So what I'm going to show today is the first step in this grand plan. So a supersonic cold stream in a hot halo, in a galactic halo, the typical conditions would be a stream with a temperature of 10,000 to 100,000 degrees. That's pretty much determined by the cooling function. Then we have the background temperature, which is just the virialized gas. So it's at around 1,000,000 degrees. And it's very reasonable to assume pressure equilibrium. So that tells us what the density contrast between the stream and the surrounding material is. That's a factor of 10 to 100. And then we can talk about the motion. So the stream is penetrating into the halo at a velocity which is approximately the virial velocity. And that is the speed of sound in the background in the surrounding material. So the Mach number defined here as v over the velocity of the speed of sound of the background is around 1. These are the two dominant parameters for this problem, delta and m, the density contrast and Mach number. Now, there could be a wide variety of instabilities that arise in such a scenario, but today I'm going to focus only on Kelvin-Helmholtz instability, which we all know and love from fluid dynamics. So the most common variant that you'll see in textbooks is just the planar incompressible vortex sheet. What that means is that you take two domains separated by a plane and give one of the fluids, say the top domain here in red, give it a velocity along the interface between the fluids. And you also assume that the velocity is much smaller than the speed of sound, so that you're in the incompressible regime, and the initial conditions are discontinuous. So you go from v here to a velocity of 0 here across an infinitesimal interval. That's the simplest variant, and you can solve that using linear analysis and get the typical time that the perturbation grows e-fold. I'm not going to dive into this formula too much. because we're interested in the more complicated variant of the Kelvin-Helmholtz instability in two important ways. The first is that we're interested in compressible flow, which is what I'm going to talk about now. And the second is, of course, the geometry, which for a stream is something much more complicated than a planar geometry. At best, you can say that it's maybe a cone or a cylinder. We have work going on that with Nir, and we should leave that for another talk because there's a lot to be said about the effects of geometry. So, just very quickly, what you do for linear analysis, you solve the equations of hydrodynamics in linearized form in both domains using the interface as a boundary condition, and you assume that your perturbations are eigenmodes of this form. So they have a sort of exponential function here, which will grow if omega has an imaginary part, as usual in these hydrodynamic instabilities. And what your goal is to find the dispersion relation, omega of k, which will depend on the density contrast delta and the Mach number n. And that will tell you how fast your perturbation is going to grow. So that was done by Landau in 1944, like any good problem in physics. And if you trace his steps, you can plot this sort of figure here with the growth rate depending on the Mach number for three different density contrasts, 1 to 1, 1 to 10, and 1 to 100. So in solid, we have the compressible solution, which I just described. And in dashed lines, we have the incompressible approximation, which is just the plain Kelvin-Helmholtz derivation. So we can see that for low Mach numbers, as you would expect, the incompressible solution is a good approximation to the compressible solution. But as you go to higher Mach numbers, the compressible solution does something strange. It peaks in the growth rate and then starts to decrease, finally stabilizing at some cutoff Mach number where the instability disappears altogether. Okay, so that covers the analytic part. If we go to numeric simulations, then the first thing you'd want to see is if your numeric simulations actually reproduce this figure that I just showed you. And that would serve as a basis for the nonlinear and more complicated physics that we're planning to attack next. So there's an interesting challenge here having to do with how you prevent short wavelength perturbations from developing significantly, but I don't have time to go into that, so I'm just going to show you a couple of short runs. So what I have here is the most simple setup that you can have. Just the delta equals 1, Mach equals half eigenmode, starting from a very small amplitude and letting it grow 20-fold. The color is a passive tracer that you can add very easily in Ramsey's. And so we see the perturbations growing, and if we take a look at the final frame, then we have the classic Kelvin-Helmholtz picture. Now, if we go to the higher density contrast, and the higher Mach number, delta equals 10 and Mach equals 1.5, then we see pretty much the same picture, but somewhat different morphology here in the final frame. That's very characteristic of the high Mach number, high density contrast. Now, if we take a bunch of these runs and compare the growth rates there to the linear analysis, then we see very good fit between the Ramsey's results here in circles and the linear analysis prediction, to within about 10% in most cases, which is very nice for a range of density contrasts 1 to 100. Okay, so very quickly, astrophysical implications of this work. What I have plotted here is a color map in the delta M parameter space. And basically, we have the virial crossing time, the time it takes to get from the virial radius to the center, divided by the time it takes for the instability to develop. So more red is more unstable, blue is less unstable. But the important thing is that we have a stable region where all perturbations do not grow, this white area here. And you can see that for the range of values that we're interested in, stability would critically depend on what side of this line you are. So for example, delta equals 80, at Mach equals 1, you're unstable, and at Mach equals 1.5, you're stable. So if we just plot the general area where we expect to find cold flows in galactic halos, you can see that depending on if Mach is greater or smaller than 1.3, 1.4, you're going to be either stable or unstable. Okay, so I'll skip the summary and just 30 seconds of what we're planning to do next. The immediate next step would be nonlinear evolution. Take a look at what happens when you go beyond the linear regime, and also what happens when you start from a nonlinear perturbation. And in the longer term, we ideally want to build up to the full astrophysical problem, coming back to this picture here. So that would necessitate 3D simulations and going to a finite shear layer rather than an infinitesimal vortex sheet. That could change the wavelength dependence of the instability. And then, of course, you have to incorporate cooling early on because that's a defining feature of this problem. And then you can start talking about gravity, magnetic fields, and whatever you want else. Okay, so thank you.
I see Frank has a question.
So I'm not entirely convinced that this analysis that you're doing is applicable to describe these streams in the simulations for the following reason. Your Kelvin-Helmholtz analysis is based on the idea that there's a pure shear flow, whereas what happens in these simulations is the gas is actually flowing perpendicular towards the filaments, and then there's a shock. So basically there's a shock that basically bounds the stream, and I could imagine, without doing any analysis, that would have a big impact on the development of Kelvin-Helmholtz abilities, the fact that there's a shock as a bounding layer.
It's a good point. I think it's more valid if you look outside the virial radius at larger radii. But of course, the part of the instability we're interested in is inside the virial halo. So I think then you can pretty much assume that you have pressure equilibrium, and the small virial shock of the cylindrical collapse to the filament is insignificant compared to the pressure of the virial shock of the halo.
In your dispersion relation, you computed the time scale, but it depends somehow, the growth rate must depend somehow on the K mode of your perturbation.
Yes.
And I think what is important is to consider the thickness of the filament, and you want to see how long it takes for K modes that have the same size as the thickness of the filament, and those are very dangerous because they're going to destroy your filament. But K modes which are much smaller in length than the thickness of the filament, they are not very important.
Yes, that's also a good point. So if you want to look at really just planar instability, then of course you can only talk about wavelengths that are much smaller than the thickness of the stream. And in that case, you have a sort of universal dispersion relation that depends very simply on the wavelength. It's just the growth time is linear in the wavelength. But the work that Nir has been doing has showed us that indeed there's something special that happens when you're approaching the scale of the width of the stream when you consider a slab or a cylindrical geometry. So for sure that will be very important in affecting the outcome of the instability.
If there aren't any further questions for Dan,